Last time, so let me share my screen. And then last time I had stopped here, I think, with uh, where I described uh, the type 1 supernova, type 1A supernova. This is the type of supernova uh, that happens when a white dwarf companion in a binary system of stars accretes matter, which is seen in the bottom left corner. So this the companion is white dwarf, and this is the companion star, red star, which is its companion, which has become a red giant, and the mass from it spills over, and the white dwarf accretes, and then that when it reaches the critical mass of, say, Chandrasekhar mass limit, then the electron degeneracy pressure cannot support it anymore. And there's an ignition because the high temperature of accretion starts a fusion reaction, and because of degeneracy, the pressure cannot be lifted, it cannot be regulated, so it's detonation. So the white dwarf basically destroys itself, and we call it a type 1A supernova. So at this time, probably it's good to introduce the other type of supernovae, all kinds of supernovae. And today, I would like to talk about supernovae in general. So first, supernovae are classified according to the lines from different ions, different elements that are seen in the spectrum. So the broadly, first of all, divided into two categories. Let me see here. So if you don't see any hydrogen lines, it's called type 1. If it's called type 1A when you see silicon lines, and this is meant this we can infer that this is because of a detonation of a white dwarf, because the carbon and oxygen in the white dwarf core uh, fuses into heavier and heavier elements, and silicon is one of the intermediate mass elements. If you don't see any silicon lines, then we call it type 1b. If you see helium lines but no silicon lines, it's called type 1c. And if you see hydrogen lines, then they're called type 2 supernova. All these three categories, the later ones, type 1b, type 1c, and type 2, they are due to a totally different kind of phenomena where massive stars, or the core of a massive star collapses, which we'll talk about later. So type 1A is a totally different phenomena, and type 1B, 1C, type 2, they are called core collapse supernova. That's due to core collapse of massive stars. Okay, so I thought at this point, uh, uh, yeah, here is what we call a light curve of type 1A supernova, which means the variation of the light as a function of time. So it's an explosion. So suddenly the brightness of this object increases and then slowly decays. And there are phases in its decay that have been identified with, for example, this decay is caused by the light from this part of this decay of its is caused by radioactivity of radioactive nickel. This is due to radioactive cobalt, etc., etc. So you can think of the whole white dwarf, the carbon and oxygen. Most of it is carbon. Carbon is basically due to the nuclear fusion reaction, is fusing into nickel. Nickel is, by the way, nickel 56 is, by the way, the most tightly bound nucleus in which neutrons and protons are, the numbers are same, 28, 28. I thought of let's do one quick estimate kind of a question. Um, let's try to estimate the total energy that is released in a type 1A supernova. Okay, and it's going to be a very quick estimate without getting into too much details, but it will give us an idea of the physical process that is involved. So this is a question that I had posed in my class, for example, when I stood. So this is one of the homework questions. So I thought I'll just post it here. So forget about this. Ignore this, breaking up of different subsets. So usually when I pose homework question, I usually give them steps, give them the hints so that they can work it out uh, through these hints. So let's assume that the whole white dwarf, and let's say to specify its mass that it has a mass of Chandrasekhar mass, just about Chandrasekhar mass limit, okay? Because otherwise it won't detonate. So 1.4 solar mass. First, one should find out how many carbon nuclei are there, and then let's assume that all these carbon nuclei are converted into 56 nickel. The mass of nickel nucleus is 56 AMU, roughly. One can assume the mass loss and the corresponding energy released, and then one can compare this energy, the potential energy of the white dwarf, assuming some sort of a radius, say 5,000 or 10,000. So I thought, let's do this. So our mass, we have specified that mass has 1.4 solar mass, and one solar mass, remember, it's 2 times 10 to the power 33 grams. Okay, I'm going to do this in CGS. You can convert it in MKS if you want, but I'm more familiar with the CGS. Okay, so how many carbon nuclei are there? So number of 12C nuclei. Okay, how do I, in this whole white dwarf star? Let's say the Avogadro's number. Okay, I can take Avogadro's number divided by 12 AMU. That will give me the number of nuclei in 1 gram, and then I multiply by the total mass in gram. This is, and then 1.4, and that gives me, I have done this. This is of the order of 1.4, I think, 10 to the power 56. So that's the number of carbon nuclei. All right. Now, then suppose all these carbon nuclei are fusing into 56 nickel, right? So the number of nickel nuclei will be down by a factor of 12 divided by 56. I'll do the same thing, but instead of 12, I would use 56 here. So this is the number of nickel. So the total mass loss, right? This is the total mass loss. How do I estimate that? I take this total number of, right? Total number, and this is the mass deficit, is the number. And remember the efficiency of nuclear, the mass loss is like 0.1%. So 0.1 times 10 to the power minus 2, and then 56 AMU. Okay, this will be the total mass loss. This is the efficiency of nuclear energy efficiency. So a 0.1% of the total mass is lost, yeah? And that gives me, if you work out, I had worked out a few minutes ago, that gives you this many grams. And then mc square would give you a total energy from here. mc square will give you and 1.5 10 to the power 53 ergs, ergs. And if you compare this with the potential energy of a white dwarf star, take this mass and a radius of say 10,000 kilometer or even 5,000 kilometer, you will find of the order of 10 to the power 51 erg. Okay, so this is much more than the potential energy. So what's going to happen is that the total, the white dwarf star is going to be destroyed totally. Okay. So that's just a quick estimate. Let me ask you another question. Once this nuclear fusion reaction is ignited, how long does it take to destroy the star? Can anyone give me an idea how to do this estimate? Timescales. This timescale, by the way, is not going to be free fall timescale, because here we're talking about the timescale for the detonation, the ignition, to basically cover the whole volume of the star, and it's nothing to do with gravity here. So let me argue that once the ignition has happened, then there's going to be some pressure difference, a pressure disturbance, and the information regarding the ignition is going to travel across the star with the speed of the the speed of the sound there, right? Whatever this sound speed is. Right? And then I can write that the typical this is the radius of the white dwarf, and whatever the sound speed is, that is going to be the time scale over which the detonation is going to engulf the whole star. What is the sound speed here? The sound speed, we know that's typically, this is how we define. So roughly speaking, I can write just P over rho. What is the pressure? Mean pressure inside a white dwarf star. Remember, we had done after virial theorem, I had worked it out, and I said this is basically 1/3 of gm square over r divided by volume. Or P mean pressure times volume is 1/3 of gm square over r from the virial theorem. So that we can use here and say the volume is gm square over r, and volume is 4 pi 3 r cube. So right, no, so what am I doing? R cube should be here, right? So then I have gm square 4 pi r to the power 4. That's my pressure, right? And then and rho, of course, is m over 4 pi 3 r cube, mass divided by volume. And so P over rho, inside this square root, I will have gm square over 4 pi r to the power 4 from pressure, and from density, I will have 3 times m 4 pi r cube, right? So 4 pi can cancel, r cube is cancelled. I'm going to single power of r will remain, m is going to cancel, and single power of m will remain. So I will have gm over 3r. Right? That's the sound speed. Right? And if you use the Chandrasekhar mass limit and star, a white dwarf star, 1.4 solar mass, and a radius say r of 10,000 kilometers, then you will get a speed, I have worked it out, of it's about this much, right? And so time of detonation, this will be equal to 10,000 kilometers, which means in centimeters it's 10 to the power 9, and 2.5 10 to the power 8 seconds. So that's about 4 seconds. See, so it's going to be very fast. Within a few seconds, the whole star is going to be engulfed in this by this detonation, right? Interestingly, by the way, if you look at this sound speed and look at this time, detonation time. So time of detonation, I'll just write it like this: r divided by gm 3r, right? That's the speed here. That's the speed. And so I should write in one way, I'll write r downstairs 3r gm, right? If I take this r inside, then you'll see I'll get something like gm, right? Now this is very close to, see, m over 3r cube, that is roughly it's very close to square root of 0. There are factors of 3, square root of 3 and 4 pi will be missing here, but you see that m over r cube is density. So this is, it just happens to be also the free fall time scale, the dynamical time scale. Okay, it's a very interesting coincidence here. Okay, so I thought I'll do this quick estimate so that sometimes it's useful to do these exercises to the students so that they get familiar with putting the numbers and not just look at the derivations. And the numbers are sometimes very interesting. If they can work out, this sort of time scales, it gives them, enables them to think quantitatively. Okay, so I'll stop sharing this. So this exercise is from Dan Mao's book, and I mentioned that earlier. That book has very nice exercises. Okay, I'll go back to my slide.
Sir,
Yes.
sir.
Yes.
So therefore, can we say that the free fall time scale is equal to this detonation time scale? I mean, we can use wherever it is required. I mean, both scales are.
No. Actually, one should not talk about the free fall time scale here, because remember we argued the free fall time scale is the dynamical time scale when gravity is dominating the dynamics. Here, gravity is not. It's the detonation is dominating the dynamic. Okay, but it just so happens. I didn't want to confuse you by bringing in that. It just so happens. It's just a coincidence.
Okay, sir.
Okay, so
Professor Nath, can I ask a simple question?
Yes.
This time it was calculated about 4 seconds. So all the nuclear fusion process of carbon going to nickel, is this happening in this short time itself? I mean, so many tunneling process probably that has to be there.
Yeah, but there's so many nuclei also there.
Okay, so tunneling time actually so very small here. I mean, I don't know. I mean, tunneling time we never hear of.
So not all of this is going to get converted into nickel. Okay.
I mean that is actually giving the total energy. So I mean, a large part.
So that is also that is a very, very rough estimate I had done. Just suppose we estimate. Sometimes we take limits in order to do quick estimates. If you want to do a real calculation,
so all these fusion processes is also taking place in that short time.
Yes.
Okay. Thank you.
Yes, sure. And remember, this it's a very, very high energetic process. So it's creating very high energetic nuclei, which increases the tunneling probability.
Yeah, that's true.
Right. Okay. So that's as far as I wanted to talk about the type 1A supernova.
So excuse me, I had one more question. You had also mentioned earlier that that iron is the most stablest. So in this explosion, it is possible that elements beyond iron also get, because so much energy.
Yes.
That is not produced, or rather probably used.
Right. So the energy produced from derived from the explosion drives also the post-iron fusion, because in those fusion you require energy.
Yes.
Right? So, and that energy is derived from this
this explosion.
Yes. And that's also going to happen in the type 2 supernova that I want to discuss now. So you're right. So otherwise, so that's how all the elements in the universe which are beyond iron, like lead and etc., are produced in the universe in supernovae.
Okay.
Yeah. Without supernovae, we won't be able to. There won't have been any post iron nuclei.
Oh, there are no other natural process by which you can
No. That's amazing, isn't it?
Amazing, actually.
Yes.
Yeah.
So let's go back to our HR diagram, and we had talked about this is the one solar mass, and these are the tracks for heavier stars, heavier stars. Now, in the case of mass more than say 8 solar masses or so, what happens, the nuclear reactions continue beyond helium, carbon, and so these are these sort of some typical examples of the nuclear reactions that happen in massive stars cores. So helium, the oxygen is synthesized, neon is synthesized, and then even carbon is burned to produce neon, then sodium, magnesium, and then it goes on, all right? Silicon, etc., etc. And each subsequent reactions, if you remember, the reaction rates actually increase with Z, and so and so become faster and faster to exhaust the fuel. And to give you an example, if you take a 25 solar mass star, the duration of hydrogen burning is about 5 million years. Helium burns in 500,000 years. Carbon is burned, all of the carbon is exhausted in 500 years. Neon in 1 year, and all the silicon is exhausted in 1 day. Okay, so the temperatures are increasing, the nuclear reaction rates are increasing, and it's like the nuclear reaction, it's devouring itself, you know, and producing all these heavier and heavier elements. And so so this is the binding energy curve, per nucleon curve, and this is where nucleon iron is, which is the most stable element, and so it stops. This can go on till about the whole core becomes iron, right? After that, it's going to stop. Now, and at that point, what happens? The whole star acquires what we call an onion shell kind of a structure. So the core has produced iron. Right after around that, you'll have silicon, then oxygen, then carbon, then helium, and at the very outer layer there will be hydrogen, right? So and of course there'll be fusions are happening in the shell burning, right? So there is an onion kind of a structure for the star, and the core has become now, say, full of iron, right? Once iron is reached, fused, then fusion reaction to produce more energy is impossible, and so nuclear fusion then stops, because to go beyond iron you require energy, right? It's like an endothermic reaction kind of thing. So what happens at this point? There are a few things happen at this point. One is the process of nuclear photodisintegration. So at the very high temperature of the core, what happens, photons start destroying the heavy nuclei. And these are some examples. For example, photons destroy the iron nuclei it has just produced into, say, helium. So each of these reactions, which consume about 124 MeV, then even the helium nuclei is destroyed back to protons, and each of these reactions will contain about 29 MeV. And so the total energy consumed per nucleon is 124, and 13 times this divided by 56. And then so about this many ergs per nucleon. And since a 1 solar mass core, suppose you take a 1 solar mass or 1.4 solar mass core, there are about, how many nucleons are there? You can find out it's about 10 to the power 57 nucleons. And the total energy loss, if you multiply 10 to the 57 by this, is about 10 to the 52 ergs. Okay, and that's actually so this is released. This much energy is released because of the photo disintegration, right? This is, by the way, more than 10 times the total energy radiated by the sun in 10 billion years, right? Another process that is going to happen is the neutronization of the core. At this high density, the inverse beta decay is going to convert the protons into neutrons in the core and release electron neutrinos. And so because of this, what's going to, so proton plus electron, right? And then there's going to produce a neutron. So electron degeneracy pressure is lost then, whatever was holding up, whatever might hold up, it's lost. So the core collapses. Because first of all, because of this huge amount of energy loss and the loss of pressure due to electron degeneracy pressure, the core collapses. Was a time scale here? The typical core density around this time is 10 to the power 9, a billion gram per cc. And 1 over square root of 0 will give you a free fall time scale of about a fraction of a second, right? So within a fraction of a second, this core is going to collapse, right? After this iron core is happens, so within a fraction of a second. And then at that point, what's going to happen is that now the whole core has become full of neutrons. It's become a sea of neutrons, right? Neutrons closely packed in a small volume. And so neutron degeneracy pressure, because neutron is also Fermion, like electrons, they also obey Pauli's exclusion principle. So if you want to pack too many neutrons in a small volume, there's going to be a repulsion kind of a pressure, right? And that is what we call the neutron degeneracy pressure. It's similar to electron degeneracy pressure. And you can, estimate the mass. So this is going to be non-relativistic degeneracy. So just like we had a mass radius relation, here also you can work out the mass radius relation of a neutron star. Okay, what you to just replace in that expression the mass of electron by mass of neutron, because now that's a relevant mass. Okay, and also Z over A is not going to be half now, because the relevant particle is neutron, and the number the whole star is neutron. So the number of neutrons per neutron is 1. So Z over 1 is 1, and you just replace this electron mass of electron by mass of neutron. You will get a mass radius relationship of neutron stars. So for a star or the core which is just beyond the Chandrasekhar mass limit, 1.4 solar mass, you will get a radius of about 14 kilometers from this very rough estimate. Okay, but that's a rough estimate, because what it turns out that Newtonian gravity is not adequate here. Remember, I mentioned that if you work out the escape speed, in this case, it becomes almost 20% of the speed of light. So you have to use general theory of relativity. And also, the equation of state is sort of uncertain here, because you're talking about equation of state of matter at nuclear density, which is not known. And so all this uncertainty, and so this is going to be decreased to about 10 kilometers. But it's still a matter of research, because we don't know the nuclear equation of state. At any rate, but this is of the order of 10 kilometers, which means if our sun were to become a neutron star, it will become the size of a big city, right? 10 kilometers. 500 times smaller in size than a white dwarf. So the sun were to become a white dwarf, remember we said it will become an Earth-size volume, the size of a planet, Earth-size planet. And if it were to become a neutron star, it will become the size of a city, right? And just like doing this manipulation of changing electron mass to neutron mass, you can say that, can we then also just use Chandrasekhar mass limit formula, but instead of now use proton mass or neutron mass, which is similar, and then use the same? Then if you were to do that, you will get for Z over A1, you'll get a number like 5.6 solar mass. But again, this is not correct, because one has to use general relativity. And of course, the uncertainty regarding the equation of state is there. So again, this is a topic of research, that what is the maximum mass limit of neutron star? And then last time there were some questions also. And this is of the order of 3 to 3.5 solar mass, I think. I'm not really an expert in this, but this is the sort of number one gets. Here, it might be interesting to tell the students that, because the students are probably going to be familiar in that quantum mechanics class. There's a portion of nuclear physics, and in the nuclear physics portion, they are familiar with this curve of number of protons and number of neutrons. Okay, and one can say that in this parameter space, you can think of neutron stars as huge nucleus composed only of neutrons. So if you plot the number of neutrons and number of protons in a nucleus, these are the nuclei that we get on familiar nuclei from the periodic table. And on the very extreme, you can think of a neutron star. In fact, this is something that I do in the class. I don't know whether you would want to do this, because the students are familiar with liquid drop model from their nuclear physics curriculum. And so this is something that I like doing, to just estimate what is the largest nucleus you can have from. So suppose, remember the binding energy expression from liquid drop model, right? This is the different terms. One has the volume term, then the surface term, and this is the Coulomb repulsion term, and this is the asymmetric term, and the different coefficients are like this. Now, one can say, suppose I don't have any protons, I only have neutrons. So Z is equal to 0 and A is equal to N, right? N is the total number of neutrons. Then this term will be 0 because there's no proton here. So Coulomb repulsion doesn't exist. So this term goes to 0. I only have this term and this term and this term, right? And which can be written as this. And the first and the last term can be combined, and then there's a surface term. This is from the surface tension of liquid drop, right? Remains like this. But if you have a very large nuclei, then you have to add gravitational attraction, which we usually ignore in the case of periodic table nucleus. But if you want to have very large nuclei, then you should add gravitational potential energy of due to all the neutrons. But you can do, suppose, remember the radius of nucleus goes as a to the power 1/3. Let's do the same thing, and we can add a gravitational potential energy to the binding energy term, right? Then we can write this, and then it becomes like this. Now, this term, look at the powers of n. This is n to the power 5/3. This is n to the power 1. This is very small, 10 to the power only 2/3. So this term does not dominate. It's not very important. Okay. So let's say that for a quick estimate, I put the binding energy to be 0, which means that this is just about the limit of what is possible. And which means I will put this minus this is equal to 0, and I ignore this second term, middle term. And then if I put b is equal to 0, which means I would just equate first term with third term, right? And then you will see that you can actually find the number of neutrons for that kind of a configuration, which turns out to be like this, 4 times 10 to the power 55. Of course, actual neutron stars are not really liquid drops. There's a very complicated structure. So what the numbers you will get is slightly more than this. So you will get about 10 to the power 57 or so. Now, 10 to the power 57 means what? It's a stellar mass, 1 solar mass. So you can actually take the students from the nuclear physics curriculum to astrophysics, right? From the binding energy arguments, okay? And you can make them think of neutron star as a large nucleus, okay? Which sometimes it's fun.
Sir, will there not be any pairing term which?
Yeah. I have.
A to the power minus
yes,
1.354.
Yes, I have dropped that pairing term. It's not very important.
Okay.
Right. Okay. You're right. Absolutely. So I have, the AP I have dropped. Okay. But this is just a quick estimates, so that the students sometimes when they do quantum mechanics, they are only thinking of one small thing. And sometimes connecting one part of physics to another part of physics opens up windows and makes the students very interested and get excited into, oh, there are connections between all fields of science, physics, like statistical thermodynamics with astrophysics, with nuclear physics. In fact, I had thought of teaching the whole nuclear physics in undergraduate section by giving examples from astrophysics. Because nuclear physics is so important for astrophysics, you can actually inspire them by giving examples. Anyway, let's go back to our. So that's what happens in the core then, in the neutron star, right? It collapses, and so what will happen? So the fall, it's a neutron star is collapsing, the core. The whole star then starts collapsing, right? And by the time, the neutron, let's go back up again. By the time this has happened, the core has become iron core, and the nuclear fusion reaction has stopped in the core. The whole star is going to then collapse because radiation is not being produced, and so the whole star is going to collapse. And what is going to happen is that it's going to rebound because iron core is still there, and it's going to rebound back. And so there's going to be implosion, which is going to destroy the whole. So a reverse shock is going to travel throughout the star and destroy the whole star. In the meantime, the iron core is also going to collapse to a neutron star. So the iron core has collapsed into a neutron star. The whole star collapses onto the neutron star and then goes back up again. The whole star is destroyed. You can think of, sometimes I give this analogy in the class, that, there's a huge queue inside, outside, say, movie theater of a very popular movie, and then everybody is trying to go in, and then suddenly the ticket counter is stopped because it's houseful. They've right, and then suddenly the ticket counter is stopped here, and then the people outside, they won't know, they will still try to go inside, but the people, there's going to be a pressure, and then the whole queue is going to be destroyed. Okay, and that's how the whole star is going to be destroyed. And here's an animation of what happens. So in the core, and this is at the right hand side, the brightness is seen. There's going to be this is going to be a flash, and then the whole star is going to then destroyed, and the explosion is then going through the star. So that's a core collapse supernova. That's the type 2 supernova. If there is still hydrogen left in the surface layers, it's a type 2 supernova because you see hydrogen lines. If the hydrogen layer has been shed before this event, then you would see type 1b or type 1c. Let's see, right. The total binding energy of a neutron star is of this order, 5 times 10 to the minus 53 ergs. This is larger than that of a white dwarf star because its size is smaller. The kinetic energy of the supernova shock, which has been estimated from observations, is of the order of 10 to the power 51 ergs. And 1% of this energy is seen as radiation, but most of the energy is carried away by the neutrino or antineutrino, which are produced during the production of the neutron star in the core. Remember, the inverse beta decay is happening, and so there's a lot of neutrinos, antineutrinos are going to be produced, and also the photons are going to produce electron-positron pairs, which are going to produce again neutrino, antineutrino. So huge amount of neutrinos, antineutrinos of 3 flavors, okay, are going to be produced. These neutrinos then help push the shock. So the shock wave, as it travels through the star, it stalls because there's a lot of energy loss due to various things. One is that, again, throughout the star, the photo disintegration is going to happen. The heavier nuclei are going to get destroyed into smaller and smaller nuclei. The shock stalls, but the neutrinos then push the shock, because if you work out the mean free path is going to be smaller than the size of the star, and so the neutrinos are going to get stopped. And so since the mean free path is smaller than the star, so it basically pushes away. And we know that this is not just theoretical expectations. We know that this is actually what happens in a supernova, and a chance occurrence of a supernova very close by in a satellite galaxy, the LMC, the Large Magellanic Cloud. This is a Large Magellanic Cloud, and this is a picture of before after kind of thing. This is the explosion that was spotted in 1987. And so that's the supernova 1987A, and it was the antineutrino were seen. The electron antineutrinos were collected in Kamiokande 2 in Japan. So you can see that this is the background level of neutrinos, and suddenly there was a spike. The spike due to the neutrinos from supernova 87A, and so integrated over time, there were about 2 times 10 to the power minus 2 times 10 to the 9 per centimeter square fluence, and each of them had 20 MeV. So in terms of ergs, this is erg, and multiplied by 6, because they just detected electron antineutrino, but there are 6 of them. 3 flavors, and each would have neutrino. And then if you multiply by 4 pi r square the distance, you would give the total energy involved in this explosion carried by the neutrinos, and that turns out to be of the order of 10^53, which is so very close to the theoretical estimate of the total energy involved in making the neutron star, which is released as supernova. So that makes us believe that the basic physics is correct from these observations. Okay. I thought okay, so let me also and the explosion, the energy of the explosion then creates all the other elements beyond iron. There are very complicated, the nuclear processes that happens. It was first discovered by carried out by William Fowler, who also got the Nobel Prize. This is the stamp in honor of the Nobel Prize given to William Fowler, and the design actually comes from the atomic neutron number plot. So these are this is the process by which the different nuclei are produced during the supernova. Okay, and so at the time of the supernova, all that has been synthesized. Remember, in the onion structure of the star, all this is going to be expelled into the space, interstellar space, basically. All these elements which have been fused by the star during its lifetime, and the nuclei which are fused during the supernova beyond iron, all these are going to be then ejected in a huge explosion. The speed of the ejecta is of the order of 10,000 kilometers per second. 10,000 kilometers per second, by the way. All right. And this huge amount of stellar material is ejected in this explosion, and that basically then fills up the interstellar space, from which maybe a later generation star would form, which would then contain all these synthesized elements, and maybe planets would form around the star, and that's how we have. So remember what Carl Sagan used to say: the nitrogen in our DNA, calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff. This is an example. This is a picture of the Crab Nebula. This is in the Cancer constellation. This is estimated to have happened. This supernova estimated to have happened in 1054 AD, 1054 AD, roughly 1,000 years ago. And this has been recorded by Chinese astronomers. They saw that there's a huge, basically there's a guest star. They didn't know. So they saw a new star appearing in the sky. I mean, there's nothing there. And then suddenly there was a star. And so they called it a guest star. And so many such supernovas, this is a supernova remnant. Okay. And so there are many such supernova remnants which have been discovered, and some of them have been traced back to historical records. For example, there is one supernova of 1006 AD, which was noticed by Egyptians, and there are many other supernova remnants which have been since then observed. And so that's another field of research, what supernova remnants do. And so next time in my last class, then I'll talk about what happens to the core, the neutron star core. So there is a neutron star at the core of this Crab Nebula, which has been discovered, which have been detected in radio waves. And we'll talk about, so these are pulsars. So we'll talk about pulsars on next class. So this is 1987A. So since its discovery, this is the 1987A at the moment before and after the explosion. And since then it has been monitored. The explosion itself is going on. And it's now been almost, how many years now? Yeah, close to 35 years, 32 years. So I'll stop with this overview of what we have learned so far. This is sort of a good summary of what happens to the stars as a function of their mass. So this mass is plotted in y-axis, and this is time on the x-axis. For low mass stars, say, so this is for stars below 0.1 or 0.08 solar mass. They never ignite the thermonuclear reactions. So these are like failed stars. We call them brown dwarfs. Right? Sun is somewhere here. So so as a function of mass, so for these masses, so this is the deuterium burning, is the main sequence hydrogen burning. And so for the sun, it will basically, what will happen? Sun is somewhere here, 1 solar mass. So first deuterium burning, and then for 10 to the power 10 years, which means 10 billion years, which we have estimated, it will go on burning hydrogen in the main sequence, and then it will become a carbon-oxygen white dwarf. There'll be a bit of helium burning, which will form a carbon and oxygen white dwarf, right? As you increase the mass, you decrease the time. Remember, the lifetime on the main sequence goes as 1 over n cube. So as you go to heavier and heavier stars, the lifetime on the main sequence is shorter and shorter. So for an 8 solar mass star, it finishes hydrogen burning in about 100 million years, then a bit of helium burning, then carbon, and then it becomes a neutron star, right? So the core. So from 8 to 10, 20 solar mass, initial solar mass, right? So then these becomes neutron stars. And beyond, if the initial star has mass more than 20 solar mass, then it's believed that the core is going to be more than 3 solar masses. So, and so the core cannot be a neutron star, right? It has to form a black hole, because for those stars, the core mass is going to exceed the maximum allowed mass of neutron stars. Right. So these are the different possibilities of the stars as the end stages of a star. If the star is less than say about half a solar mass, then it ends up with just a helium white dwarf, because it never goes into the helium burning. It just finishes hydrogen burning and then becomes a helium white dwarf star. For stars between half a solar mass and 8 solar mass, the end stage is a carbon-oxygen mix white dwarf. If the star is more than, initial mass is more than 8 solar mass. So here, remember, the core, the white dwarf mass is less than 1.4, right? White dwarf cannot be more than 1.4. So notice the difference between the core mass and the initial mass, right? Core mass is much less, right? And if the total mass is more than 8 solar mass, then it cannot be a white dwarf star. It has to have a neutron star, and beyond 20 or 30, and that's a sort of an uncertain kind of thing here. There are debates. People debate about this cutoff. About is it 20? Is it 30? That's uncertain. Okay, it's just. So beyond a certain mass, say 25 or 30 or 20, the end stage cannot be a neutron star, it has to be a black hole. So these are the times, these are the end stages, this is the time scale over which they reach the end stages, and this is the mass. So this is a good summary of whatever we have done so far with the stellar evolution. And I would stop here because there's only 5 minutes remaining and I don't want to get into a whole new topic of pulsars. So I'll take questions. And
sir?
Yes. Okay, there's a question here.
Whether I have missed it, but sir, what is nova? I mean,
so nova, yeah. So so there are small explosions that can happen when the mass accretes, which does not detonate the whole star, which does not destroy the whole star. So these are small explosions that happens because of accretion in a binary system. So these are called nova. And there are recurring novas. The mass can keep accreting onto, and then, but for some reason, the whole star is not destroyed, detonated. When the whole star is detonated, we call it supernova.
Okay, sir.
Any other question?
I mean, sir, nova for a star to become a nova, this accretion must be there.
From a binary system, yes, yes, yes.
So that can happen only in the binary system.
Yes, as far as I know, yes.
Sir,
so,
there is one question.
Yes.
Neutron has a lifetime of around 11 minutes, I suppose. So how does it affect this structure of neutron star? And
what neutron has a lifetime? What?
About 11 minutes, if I remember correctly.
That's a free neutron.
Yeah.
But these are not free neutrons.
Oh, okay.
Yes. Yes. The structure of a neutron star is much more complicated, and I'm not an expert in neutron stars, so maybe you can read up some articles there on neutron star. There is. Are you aware of this science education journal that is published by the Indian Academy of Science called Resonance? Sometimes it has articles.
Yes, sir.
Right, and I think a few years ago there was an article on neutron star structures by Sushant Konar, who is in NCRA now, which is a very good article. If you can get hold of that.
Okay, sir.
Yeah. So those articles are actually written for targeted towards BSc and MSc students, which are very good pedagogical resource material also.
Okay, sir. Thank you.
Yeah.
Sir, white dwarf or neutron star or black holes, all these are stable structures.
in stable state?
Yes, yes. Well, I mean, see, white dwarf is a stable state in the sense that it's just going to cool, radiate, and lose energy slowly. So does a neutron star. Okay. So in that way, it's stable in the sense that gravity is being balanced by something. In white dwarf, gravity is balanced by electron degeneracy pressure. In neutron star, gravity is balanced by neutron degeneracy pressure. Right? And black hole is of course, is a completely different beast. It's beyond redemption.
So there's another question, like we have heard that these neutron stars, pulsars are essentially neutron stars.
Yes.
So it comes from the rotation part. We had that in the first set of lectures.
Let's discuss this.
My question is that when stars form, initially there will be some angular momentum, right? So this rotation is a property of all stars, right? Like see, the sun rotates. So when it becomes a white dwarf, is the rotation still preserved? When it becomes a neutron star, is it still preserved?
Yes. You can in fact connect all this through just conservation of angular momentum. Maybe let's do that in our next class. Shall we do that?
Acha. So basically stars by and large will also be rotating. Can we generalize it like that?
Yes. I mean, in fact, you can think of it like this. This is how I think. I mean, it's very very kind of unrealistic to think of something that is not going to rotate. I mean, let's say the star, right? The star is going to form from interstellar cloud.
Yeah.
Right. And even if the interstellar cloud has even a very small rotation, when star collapses and it forms. So if the interstellar cloud has even a small amount of rotation, when it contracts to form, shrinks to form a star, just because of angular momentum conservation, the star is going to have some appreciable rotation speed.
Okay. Okay, sir.
Even galaxies have rotations, right? The galaxies.
That's why. That's okay.
Right.
And
so you can think of the galaxies were formed out of again, spherical balls of gas, right? Now you can actually think of how is the primordial angular momentum generated. And so one can think of tidal torque. So suppose I have two extended objects and they have relative speed, right? You can imagine that the one is going to produce torque in the other and the opposite torque in other. So as they pass by one another, if it's an extended object, just from tidal forces, you can induce rotation. Total angular momentum is going to be conserved. Right, but you're going to then produce some a bit amount of rotations, and this is how. So this is called the tidal torque generation and angular momentum generation, and then the galaxies will also have angular momentum. There's a distribution of angular momentum in galaxies.
Thank you, sir. Yeah, that kind of explains why things rotate. And talking about this brown dwarf. Stars that were just not formed. So some of these huge planets that we see, could they have become stars or didn't become
for example, you can think of Jupiter. You can think of Jupiter. It's not a brown dwarf, but Jupiter had been slightly more massive. Since Jupiter is about, if you compare the mass of Jupiter to Sun, it's about 1,000th. Okay. And so remember the brown dwarf limit is about like a 1/10 or 1/10.
Yeah, 0.8 or so. Yeah,
right.
Correct.
Right. So the Jupiter has missed. Jupiter had been 100 times more massive. 100 times more massive. It would have been a star.
Oh. Yeah. So we would have had a binary system then in our.
Yes. We would have had two stars.
Very, very interesting. Thank you, sir. Good.
Sir, regarding this conservation of angular momentum, we observe this differential rotation. So does it get conserved when this neutron star or white dwarf is made? Like how does it get reflected? in final stages, this differential rotation phenomena?
That's a question I have not really thought about. You know, one can take the total angular momentum and then see just the if it is conserved, then if a star like the sun were to be compressed into a neutron star, then what would be the rotation field? But see, neutron star is a solid body kind of thing. This is not going to retain its differential rotation. You cannot have differential rotation in a solid body.
Okay.
Because then there are other forces. I mean, it's not just gravity. It's because there are going to be electromagnetic forces for a solid body. These are crystalline structures in a way. A white dwarf has a crystal structure. So, so it's not just a gaseous plasma in the case of a sun, right? So the differential rotation is not possible in solid bodies.
So it's kind of integrated in those systems. So you just find the whole body rotating at some final angular momentum kind of thing.
So in the next class, then I'll just mention a few things about the neutron stars. But it seems that you already have done, some of you have done pulsars. So I'll see what we can do. Maybe we can talk about some exercises from what we have done.
Yeah, in the first part of the lectures also we had some basic introduction to pulsars, sir.
Okay, right. Okay, okay.
When the overall thing was also about first on different messengers and all that. Yeah.
Okay, okay.
Yeah, that was at a very introductory level. So, Biman, if you want to do a bit on pulsars, it would not be bad, and then discuss other things as well, I think.
And then discuss some exercises. Then I think it would be nice to do some exercises based on whatever we have done.
Yeah.
Maybe you can just pick up some exercises from Dan Mao's book or Carlos Lee's book, and then just work out.
Yeah, that's how I remember that rotating, that lighthouse effect sir talked of.
Okay, then.
The journal which Biman has mentioned, that is something which you could easily access via the Academy website. Nowadays, it's jointly published by Springer and the Academy, but all previous issues, if you just Google Indian Academy of Sciences resonance, you'll be able to get out of previous issues. The other thing I will do is, after Tuesday's lecture, is that Dipankar also gave a set of lectures on physics of compact objects. This is Dipankar Bhattacharya from Ayuka. So I'll send you all the link so that later you all can actually at your leisure listen to his presentations as well, which is slightly more advanced, but it will build on what Biman has done over here. I'll do that later. And I don't know if the mail has gone out as yet, but like we discussed last time, we have put the questions along with the answers given in the Google Drive. So you all can download it and have a look. And if you have any questions, we can try and address them as well. Okay.